All right, today we're diving into something pretty amazing, manufacturing simulation. It's a technology that lets you build, test, and even break an entire factory all inside a computer before you ever spend a dime in the real world. Let's get into it. So let me just start with this question. What if you could see every single bottleneck, predict every inefficiency, and catch every single costly mistake in a multi-million-dollar production line before it even exists? Well, that's the promise of manufacturing simulation. Now, to really get why simulation is such a game changer, you first have to understand the incredible pressure that modern manufacturers are under. It is a whole different ballgame than it was even a couple of decades ago. Really, it's become this incredibly high-stakes race. You have to be faster, you have to be more flexible, and you have to be more efficient than ever before, just to keep your head above water. And when you look at the details, it's easy to see why. The products themselves are getting way more complex, but their shelf life, the time they're actually on the market, is getting shorter and shorter. This forces factories to make smaller batches of more varied stuff, all while keeping quality sky high and dealing with fierce global competition. There is just zero room for error. So, how in the world do you win a race like that? Well, you build a digital twin. You step into the world of simulation, where you can experiment and break things as much as you want without any real-world consequences. Okay, so the official definition here sounds a little academic, right? But the idea behind it is actually super simple. You're basically creating a working digital copy of a real thing, like a factory, so you can run experiments and learn things that you can then use back in the real world. And two words you'll hear a lot are system and model. The system, that's the real deal. All the machines, the people, the processes, all working together. The model, that's your simplified digital version. And honestly, the real art here is making that model accurate enough to be useful, but not so complicated that it's impossible to work with. And this is so important to understand. Simulation is not a one-and-done thing. It's a loop. You start with the real world, you build your model, you run your experiments, you analyze what happened, and then, this is the most important part, you take what you learned and use it to make the real system better. It's a cycle of constant improvement. So, how do you actually build one of these models? Well, tools like Tecnomatix Plant Simulation use this really powerful but, believe it or not, intuitive approach. I like to think of it as a set of digital Legos. The whole philosophy is called object-oriented modeling. So forget about writing thousands of lines of code from scratch. Instead, what you get is a library of pre-built objects. Things like machines, workers, conveyor belts, and you just piece them together like you would with Lego bricks. And here's what that looks like in practice. See on the left? That's your library of digital bricks, your components. You've got a source that makes the parts, a single proc, which is just a machine. And then on the right, you can see how they've been clicked together to make a simple production line. It's really visual. And the process really is this simple. You just drag an object from your library, you drop it onto your layout, which is called a frame, you connect the objects to show how the parts are going to move, and then you hit run and watch your digital factory come to life. Now, building with blocks is cool and it's efficient, but what makes this whole thing truly powerful, what allows it to scale up to massive, complex factories, is a concept called inheritance. This example explains it perfectly, even though it's not about factories. Let's say you create a generic parent object called patient. Then you make more specific child objects like adult and child. They automatically inherit everything from the patient parent. Now for the magic part. If you change the parent, let's say you add a new rule or behavior, bam! Every single child object gets that update instantly. Think about that in a factory. You change one master machine and all 50 identical machines in your model update automatically. That is the power of inheritance. Okay, so you've built your digital factory. That's a huge step. But building it is really just the beginning. The real goal here is to make it perfect, to find the absolute best way to run it. And that brings us to a massive challenge. I mean, a normal factory has countless variables, right? Buffer sizes, the number of workers, machine speeds. The number of possible combinations can easily run into the millions, even billions. So how on earth do you find the single best one? Well, the answer actually comes from a pretty unexpected place: biology. This is the core idea behind something called a genetic algorithm, and it works pretty much just like natural selection. The software has tools built right in, like the experiment manager and the GA wizard, that do exactly this. They run thousands of different setups automatically. They measure how well each one performs, its fitness, and then they breed the best solutions together to create a new generation of even better ones. And what you get at the end of this digital evolution is a report that gives you crystal clear, totally actionable data. It points out exactly where your bottlenecks are, which steps are eating up the most time, and where you should focus your efforts for the biggest impact. It completely takes the guesswork out of the equation. So, when you put all of this together, what does it all really mean?
Well, it signals a really fundamental shift in how we plan for pretty much any complex system.
What this technology really does is it transforms factory planning from something that was based on experience and intuition, basically guesswork, into a predictive, data-driven science. It's about knowing, not just guessing. And why should any of us care? Well, it means the stuff we buy is made with less waste. It means companies can be more efficient, which helps keep prices down. It helps them innovate faster, and ultimately, it just leads to smarter, less risky investments in the very infrastructure that powers our economy. And that brings us to one last pretty powerful thought. We've just talked about how this tech can perfect a factory. But if we can digitally design, test, and optimize something that complex, just imagine what other systems we could tackle next. Global supply chains, city traffic patterns, the way patients move through a hospital. The possibilities are absolutely fascinating, and we are just getting started.